So in this talk, I will introduce OptiSig, a method to generate and verify the semantic signatures, and this one can be useful to detect the metamorphic malware. And my name is Nguyen Anh Quynh. I'm working for Coaching. Okay, at first I will talk a little bit about the motivation behind my talk. So people in industry always criticize antivirus, or AV in short, because they cannot detect malware timely and properly. And one of the area that AV suffer most is that they cannot detect metamorphic malware. So metamorphic malware is a concept that was introduced quite a long time ago, about 15 years ago, and so many years passed, but still nowadays AV cannot detect them properly. And metamorphic malware was introduced. They introduced many interesting concepts to bypass the scanning signature employed by the AV, and this problem is still happen now. And in this research, I propose another new method, and this one is called OptiSig, and we propose to use semantic signature that's different from the current signature in the AV. And OptiSig can be used to detect the metamorphic malware. So we try to raise the bar higher so we can solve this problem somehow. So in this talk, I will first introduce the problems shortly with the current antivirus and why they have so many problems to detect the metamorphic malware. And after that, I introduce OptiSig and the concept of semantic signatures and how it can be used to detect the metamorphics. Next, I will explain how OptiSig can generate the semantic signatures. And after that, I have some live demo. Hopefully, you like it. And conclusion at the end of the talk. Okay, so malware as a program that causes damage to the computer users. And one important thing about the malware is that they propagate and multiply themselves when they infect your machine. And to detect the malware, of course, we use the antivirus or AV. And the main method for the AV to detect the malware is to use a signature. So basically, on the malware, on the AV, they have a huge database of signature, and each malware has one signature inside the database. And when the AV want to detect the malware, they will scan the suspected file with some signatures inside the database signature. And if this signature match this file, the AV can tell you that this file is infected by this malware. And the signature is for that malware. And this one thing we can see that the signature is all about syntactic. Why? Because the signature can be a range of code extracted from somewhere inside the malware, and they take it as a signature. Or more flexible, they can have another type of signature is in a regular expression form. Or they can combine with some logical combination to have a more flexible signature, and that's what Clam AV is doing. Here's one simple signature. I take this one from Clam AV. So you can see that this file, they have operation code right here. And this code, this one's malware. This code, we don't see that anywhere in the normal file, not anywhere. And this code is specific for this malware. So they take this code out and consider it a signature. So if you match this signature with a particular file, and you can match it with signature, you can see that this file is this malware, and this in this case is Georgian.exchanger. So this is the signature for Georgian.exchanger. However, you can see that the signature, like in this case, is not very flexible because with each malware you need one signature, right? So they have a more flexible signature. It's called something like regular expression. So here we have two malware, 5.exe and 7.exe, and you can see that they have some code inside. And these two codes are very similar, except 4 bytes in the middle. You see? The first part are same. The last part are same, but the 4 bytes in the middle are different. So they try to combine these two signatures into one, and they have the signature here. So they take the first part here, last part here, and somehow in the middle we have 4 bytes, and the 4 bytes can be anything. So with this regular expression signature, we can detect both 7.exe and 5.exe. So this signature can detect more than one malware, right? So it's more flexible. However, all of them are still syntactic, and there are some problems with the syntactic signatures. First, we need to update the signature for each version of one malware, because the malware, when they infect, they can change themselves. So each version of the malware, you need one signature. And because there are so many malwares, the signature database is getting bigger and become a major issue for users. The other problem is that it's very hard to catch up with a new wave of malware because there are too many malware. And we need a new signature for each malware, and that is a big problem. Finally, the syntactic signature is very easy to be evaded by the metamorphic malware. So what is a metamorphic malware? Okay, this concept was first introduced about 15 years ago in the malware named BlackHat for Windows 95. And metamorphic malware is designed specifically to defeat the syntactic signature. And you can understand that when the malware go into your machine, it tries to infect many files, as many as possible. So suppose that it infect first file and second file. So when the malware infect your file, it will inject some code into each file, right? So the idea is that the metamorphic malware, they don't inject the same code into two files. They inject two different code, even they do the same thing. So two different code transform one from another, do the same thing, but being injected by different files. And that is the concept of the metamorphic malware. So we can see that metamorphic malware introduce many problems for the syntactic signatures. Why? Because each infection by metamorphic malware, we need one separate signatures. And because in theory the metamorphic malware can generate infinite number of infection. So we should have infinite number of signatures, and that makes the signature database very huge and just understandable. And second, it's not only that the database is huge, but metamorphic malware can totally bypass the syntactic signature. Okay, here's how the metamorphic malware can defeat the syntactic signatures. So the metamorphic malware use many different techniques, but I will introduce just the most popular techniques. So they use 4 transformation techniques to infect your file. First one, they use a transformation technique named insert that code. Second one, substitute instruction with equivalent instruction. And the third transformation technique is reorder instruction. And finally, they can combine all of those 3 methods to make the code much more complicated. First one, what is the insert that code? That code here means that when you have the code and have that code inside, that code is the code that if you remove it, just nothing changes. There's no impact. That code doesn't make any impact to your code. And in insert that code method, there are small method. First one, insert that instruction. Second, insert no operation semantic instruction. The third one, insert unreachable code. And the last one, insert branch instruction to the next instruction. And now we go into each method. First one, insert dash instruction. So we can see on the left side, the original code is copy the 5555 to EDX, and when the metamorphic transforms this code, it insert another instruction. Before that, copy 30 to EDX. So you can see that this one's that instruction, right? Because below we copy 555 to EDX, so this one is that code. You can remove that. There's no problem, no impact. But you can see the transform code look very different. So you can see that the left code and the right code, they do the same thing, but syntactically they look different. Okay, another method is insert not semantic instruction. So the idea is that the malware, when they transform the code, they insert some code that actually does nothing. So here, the original code is on the left side, and when the malware transform it, it insert two instructions, one before and one after. And you can see that move from EDI to EDI does nothing, right? Move exchange CX with CX does nothing. Exchange one register with itself. So you can see that the left code and the right code looks very different, but they do the same thing, right? So the third method is insert unreachable code. And metamorphic malware uses a lot. So here you can see on the left side the original code. And here, when it transforms itself, it insert a jump label to here. And in between, it insert junk code. It can be arbitrarily long. And you can see that this junk code doesn't work. It's not executed. It's not unreachable. But you can see the left side and the right side looks so different. Even they do exactly the same thing. The last one, insert a branch instruction to the next instruction. So you can see another transformation on the right side. So you insert a jump here, jump to the next one. Actually, it does nothing, but the code looks very different. Okay, that is the first method, insert that code. A very nice transformation method for metamorphic malware. Second one, substitute instruction with equivalent instruction. So see here, one example. On the left side is the original code, and on the right side is the transform code. You can see that here, the malware try to substitute move 0 to ESI with move 1 to ESI, and after decrease it. So you can see that this one and this one, they are the same thing. Copy 0 to ESI, but it looks very different. And here, move 1, 2, 3, 4, 0, 0 to EDX, which can be done with copy 1, 2, 3, 4 and something to EDX, and after that is 0 DX, which make the last 2 by 0, right? So this one and these two instructions, they do exactly the same thing, but you can see left side and right side are very different. The third method, reorder instruction. So here also we have original code and transform code. So on the left side we have copy 0 to ESI, and after that copy something to EDX, and when they transform the code, the malware transform, they reorder these two instructions. And you can see right side and left side, they do exactly the same thing, but syntactically they are different, right? And finally, you can combine the first, the second, and the third method, each other, and you can generate a very completed code. So you can see that metamorphic malware really introduce a big problem for the original, for the legacy signature scanning AV. You can see that so far no AV can detect the metamorphic malware like this. So the question is how to detect metamorphic malware. So you can see that we have few transformation here. So we break it down and we try to solve each problem. So we want to detect the insert that code, we want to detect the substitute with equivalent instruction, we want to detect the insert branch instruction to next instruction, and finally we try to detect the reorder instruction and how to solve each of them. And if you can solve all of them, you can solve the problems. Okay, so the detecting metamorphic malware is a very hard problem, and in this research we just try to solve the core problem, not everything, but the core problem, which is that given two different code, like in the assembly form you see here, can we answer that the left code and right code they do the same thing or not? So you want the answer yes or no. We don't need the answer might be just yes or no. And if we can have the answer that the left code and the right code do the same thing, we can consider this one the signature, right? And all the code that transform from here, from this code to something else that match with this one, can be considered to be from the same malware, from the same metamorphic malware, right? So our problem here is that we try to compare two sequences of machine code, and we need the answer yes or no, is that they are equivalent or not. And here comes the OptiSig solution. So with OptiSig we propose a semantic signature, not a syntactic signature. And this one is another approach to verify the suspected file. So we propose a semantic signature to fix the problem of syntactic signature. And what is a semantic signature? Semantic signature is something that contains the semantics of the code to be verified, not the syntactic. And the advantage of semantic signature is that we can detect metamorphics that when they transform themselves, they keep the behavior unchanged. So if they keep behavior unchanged, we can detect that. And if we can detect the transform code, so we don't need to update the signature for each infection of the metamorphics anymore, right? We don't need to update the new signature for each infection. So it's very good. Okay, so here's how we create the semantic signature. First one, we create the semantic signature on the machine code, the binary code. And the signature of the code is actually the formula, the first order logic formula of the code, which expresses the semantics of the code. And after that, we use theorem prover to compare the two signatures, which are actually the two logical formulas. So you can see here on the diagram here, we have two code. This one is considered the signature for the malware. This one is the transform code. So with the signature, we generate the logical formula, and we consider this one semantic signature. And when you want to verify something with this signature, we also do the same thing. We also generate the logical formula for this code. After that, we fit these two formulas to the theorem prover, and this one can tell you these two formulas are equivalent or not, which means these two codes are equivalent or not. And if we have the yes or no question, have the answer as yes or no here, we can solve our problems. So what is a semantic signature for the code? Here are some very simple example. So basically, for the simple code like arithmetic or moving data instruction, we encode them like this. So on the left side, we have the malware code like this. Copy 48 to ESI, copy 207 to EDX, and the logical formula for this code is ESI equal to 48 and EDX equal to 207. And that is the logical formula for the left code, right? And in case the code contains the control flow, we break down the code into the control flow graph with basic block inside, and we follow the control flow. For example, here, malware code here we compare EAX to 32. If EAX is 32, we jump here and copy EDX to ECX. Otherwise, we saw ESI with ESI, right? And the logical formula consider two branch. If EAX is 32, we assign EDX to ECX. Or if EAX is not 32, we set 0 to ESI, right? That's how we create the logical formulas. And that's all. These are very simple example, but you can imagine what it does. Okay, but however, just something to be careful, because note that here we have logical formula. And can you tell me? Anybody tell me? Is there anything wrong with this? We have the code on the left side. We have logical formula for it. For it on the right side. Anything wrong here? What's wrong? What we are doing here is a logical formula, not assign 48 to ESI, not assign 207 to ESI. So that means this one is not acceptable. You cannot have 48 ESI as 48 and later ESI is 207. It's conflict in the logical formula. Logical formula doesn't accept the conflict. So what I'm doing here is not assign something to variable, but you have the formula, logical formula, and cannot be conflict, right? So how to solve this problem? Here's how we solve problem. We use a method named single static assignment, which is borrowed from compiler technique. So whenever we have the new value for the variable, we don't override it, but we create the new variable. So in this case, I create the new ESI1. So we have ESI1 equal to 48 and ESI1 ESI equal to 48 and ESI1 equal to 207. When after this, all the reference to ESI should reference to ESI1, right? So there's no more conflict, and we use single static assignment to solve the problem. So this one, we must be very careful. Okay, so it looks very nice, but there are many challenges to implement the ideas. So there are two challenges. The first, machine instruction can overlap in semantics. For example, move EBX to EAX is actually what a load effective arrest from EBX to EAX here, right? So we have a problem because the Intel instruction set are very complicated, and they have many overlap instruction, and that make analyze very complicated. The second problem is that the instruction in itself may have multiple implicit side effects. For example, push EAX, actually it does many things inside, and what it does is that it copy EAX to the stack, and after that it move ESP, the stack pointer, down 4 bytes, right? So there are many side effects inside one simple instruction. So to solve those problems, we first we need to normalize the machine code to intermediate representation language, or IR. And now we need the IR, and we need to normalize the code to IR. So we have some requirements for the IR. First, IR must be very simple, no overlap. Second, IR must express its semantics explicitly without side effect. We don't want any side effect inside the IR, right? And finally, IR should support static single assignment (SSA), because we need to generate the logic and formula from the normalized code, right? So we had 3 requirements, and here's what we work. I detail the diagram here. So first we need to translate machine code. We need to normalize the machine code to our IR. After that, somehow we need to optimize it. Later I will explain you how, why we need to optimize it. After that, from the normalized and optimized IR code here, we generate the logic and formulas. And we do the same thing with the code that we want to verify again the signatures. Everything will be fit to the theorem prover in the last step. Is it clear? So the question is that we need the IR to normalize the code. So the big question is which IR? The next step, I introduce LLVM project, and you will see why LLVM is important for OptiSig. Anybody here already heard about LLVM or used LLVM before? No? Anybody here use macOS? Do you ever write program in macOS and compile that? So the question is because nowadays the compiler on the macOS X, they all use LLVM behind as a compiler technique. And LLVM project is an open source project for the compiler, and LLVM, the rest is there. And LLVM project, they offer a set of frameworks so you can build the compiler very easily, very quickly. And the core of the LLVM is the LLVM IR. They have IR inside. And on top of the IR, we have a lot of optimization module ready to use. And everything is ready and open. So take a short look at the compiler model. Here you can see that in the normal compiler, we compile, you need to compile from source code to the machine code, right? And the compiler, actually, there are 3 components inside, 3 key components. First, the front end, which translates the source code to the IR. And after that, the compiler has a second component to optimize the IR. And after this step, the optimized IR will be compiled by the backend to the machine code. That's all the compiler is doing to compile the code for you. And here, LLVM, they use the same model, but they break 3 components here, and they create a very clean and very explicit interface between 3 components. So we have here, first we have the front end, LLVM front end. LLVM front end will compile your source code to LLVM IR, and after that, LLVM IR will be fitted to the second component, LLVM optimizer. And after that, optimizer will send the optimized IR code to the backend. And after that, backend will generate the machine code for you. And here's the LLVM model. And you can see it's important that they separate the front end, optimization, and backend. And the idea why LLVM is very useful because they introduce very clean and separately component which can be reused. So you imagine that if you want to write a new programming language, you just need to program your front end. You translate your programming language to the LLVM IR, and that's it. You don't need to do anything because after that you can reuse the optimizer already available, and you can reuse the backend already available. So what you need to do is just write your front end, and that's it. Very easy, and that make the compiler programming very much easier than before. So the core component of LLVM is the IR. So the LLVM IR is independent of the target architecture, which means it doesn't depend on your machine. It can be x86, it can be PowerPC, it can be ARM, and it's a reduced instruction set which means they have very few instructions, not like the Intel. And it's a register-based machine, and they have infinite numbers virtual register. And the register also have type like high-level programming language, like void, float, integers, and it also have pointers with type. Pointers can be integers pointer, or float pointers, or anything. And here it's important. LLVM support SSA, single static assignment by nature, by default. And the basic block of LLVM has only single entry and single exit. And finally, when you compile some source code to LLVM IR, we have LLVM bit code. Okay, next LLVM instruction. LLVM is very simple. It only introduced 31 instructions. It's very simple. Designed to be very simple and no overlap. It supports arithmetic operation and on integers and float. You can add, sub, multiple, divide, remainder. It has bitwise operation, so you can AND or SOR and anything like on Intel. It has branch instruction, which is low-level control flow. But this one, remember, is still unstructured, very similar to assembly, like what you see on the Intel. And just one thing we need to know: the branch target must be explicit. You cannot have indirect jump in LLVM area, not like in Intel. So remember that on Intel, instruction set is they allow the indirect jump, right? But on LLVM area, they don't allow that. And they have some instruction for the memory access, load, store. Some instruction for compare, and this one is to support SSA. Okay, here's a simple, very simple example. Also, here on the left side we have C code, and we compile this C code to LLVM IR on the right side. Yeah, you can see. Here is a function of LLVM IR, and here is the argument for the function. On the left side we compare if A is 0, we return B, and on the right side we have LLVM instruction. Here's a compare A to 0, and is it equal or not? If it's equal, we jump to done here. If it's not equal, we jump to the recursive here. And you can see that's the LLVM code. It looks quite simple, right? Okay, so here's another core component of LLVM architecture. That is the LLVM optimizer. And basically, we can feed the LLVM IR to the optimizer, and it can optimize the code for you. And in LLVM terminology, we call the optimizer LLVM pass. And we can combine different paths with each other. And in LLVM, there are few different kind of paths. First one, the path can be used to collect or visualize information. This one is not very important for our project. The second one is very important. So LLVM path can be used to optimize the code, to transform the bit code. And there's some others paths which we don't care about. And in the latest version of LLVM, the version 3.2, they provide 182 passes that are ready to use. So that's a lot, and we just need to use it, don't need to do anything. So here, remember, we need to choose a IR to normalize the code, right? So here, we decided that we choose LLVM IR as a language to normalize the code. So you can see that originally LLVM was introduced to for you to program your compiler, but we don't use LLVM to make the compiler, but we use LLVM to normalize the code, and after that we optimize the code. So we choose LLVM because it satisfies all the requirements for the normalization phase. And remember, we only use a subset of LVM. We don't use all the 31 instructions. We just use subset instruction. For example, you can ignore the instructions that are about the high level information that you can get from source code. But here, because we are working with a low level machine code, so we can ignore those instructions. And LVM is good because it offers you a framework, so we can process the output IR very easily. And finally, you can take the advantage of the LVM optimizer. So you can optimize the bit code, and the result bit code from this step is normalized and optimized. And you can see that we have some LVM passes that are very suitable, and those passes can be used to reverse the transformation of metamorphic malware. So here's I detail my diagram. First, we need to translate the machine code to LVM IR. This one is familiar to building the compiler front end, but this one is not for high level language, but for machine code language, low level language. It's tough because the machine code is unstructured. So for example, we must deal with the indirect branch or shell modified code, which can be available in the machine code, and it's not easy to solve. And from machine code, we build the control flow graph, and we have the control flow graph in connect the basic blocks, and we go through each block, and we translate all the instruction in each block to LLVM IR. And this step, to express the semantics of the machine code, we need to reference to the ISA manual. And in this case, I need to reference to the Intel or AMD manual. You can see. So here's one sample. We translate NEAX EBX to LLVM IR, and here is on the right side you see the LLVM code that does this. You can see it looks very complicated because we need to update the flag, right? So it's not that simple. So one Intel instruction can be translated to like 10 LVM instruction. And after that, we optimize the bit code we got from the normalization step. And here are some optimization I am using. First one, constant propagation. So this LVM pass can simplify the code here, like here. You can simplify like y equal to 22. So another optimizer is eliminate that store instruction. So we can have the simple code here, and here you can see that y equal to 3 is that code, right? And DSE pass can remove this code. Next one, another pass combine instruction. Y equal to x plus 1, z equal to y plus 2. This one is actually z equal to x plus 3. And this pass can combine this code to be a simplified code on the right side. Another pass, which is very important, is simplify control flow graph. It can be used to remove isolated basic block. It can be used to merge basic block into its predecessor if there's only one and the predecessor has only one successor. Or you can merge a basic block that only contain unconditional branch. So you see, you have 4 transformation, right? Insert that code, substitute with equivalent instruction, insert branch instruction to next instruction, and on the first 3 transformation can be solved with this LVM optimization. Like this, insert that code can be removed with DSE and simplify control flow graph. Insert branch instruction to the next instruction can be removed with simplify control flow graph. and that make us we show on the first three transformation, and what remains is the last one, reorder instruction, which cannot be shown by LVM. So next we see how we show the last transformation. So here I detail the diagram again. We generate the semantic signature from the normalized code. So here, so the semantic signature is actually a logical formula generated from the output IR of the normalization step. So we have machine code here, we normalize the code, after that we optimize, and we can remove the first three transformation. And after that we generate the semantic signatures. Right? Okay, so about the logical formula. After we have the logical formula, we need to show it. And how to show it? Here, we propose to use satisfiability modulo theories or SMT solver. So SMT solver is a theorem prover that's based on decision procedure. And SMT solver work with the logical formulas of different theories. And SMT solver is very suitable because it can express the behavior of computer program. Very suitable. And it can prove a logical formula is satisfiability or validity or not. And this one is important. The SMT solver can prove the equivalence of two logical formulas. And that's why we need it. Okay, so there are many SMT solver available on the internet, but here we use Z3 SMT solver, and this one is open source SMT solver coming from Microsoft, and they support Linux and Windows, and they provide the binding for C++ and Python. It supports bit vector theory, which is very useful to model the arithmetic and logic operation. It supports array theory, which is good to model the memory access. And finally, it supports the quantifier exist or for all. Okay, so here we have the more detailed diagram. So we have two logical formula, and we fit all of them to the theorem prover here, or SMT solver here. And these two logical formula, we want to prove the equivalence of them, right? So if we have this one and this one are equivalent, which means with the same input, same register input, we need to produce the same output, and that make it equivalent. Okay, here is one example how we go from machine code to the logical formula. So on the top we have the machine code here, and we after the normalization and optimization step, we have this code, and from this code we generate the logical formula, which come here in the last box, and this logical formula will be fitted to the Z3, and you can show it. Okay, so you can see that the last remaining transformation that was not shown by LVM can be shown by SMT solver. Why? Here, we have the signature and the malware code here. You can see that the malware is just reorder the two instruction in the signature, right? And with the signature, we have this logical formula. And with the reorder instruction code, we have another logical formula. And you can see this one and this one, they do the same thing. And the SMT solver can show that it can tell us that this one and this one are equivalent. It can do this work very well. So we show the last transformation, reorder instruction. Okay, so that's our idea for OptiSig, and we implemented that. We have the web interface for demo, and we have framework to generate the signature for machine code, and we can compare the signatures. And OptiSig now we support the 32-bit and 64-bit for Intel platform, and we use Z3 server to process logical formulas. And the project was implemented in Python and C++, and it takes about 5,000 lines of code. Okay, here comes the interesting part, the demo. Okay, so the web-based demo. You can see that. So it sounds very simple. We have two boxes here. So I will pass two machine code to assembly code on the left side and on the right side. After that, I click this button, and it can tell me this code and this code are equivalent or not. Okay, you can see two assembly code. They look very different. The right code looks very simple, and the left code looks very complicated. And actually, the code on the left side, they use many transformation method to make the code very long, very complicated. But actually, they do the same thing. The code on the left side was transformed from the code on the right side. So, I have some option here. I can select the assembly syntax. It can be, the code can be copied from IDA or from NASMR, and I can choose 32-bit or 64-bit here and verify equivalent. You see that? The left code and the right code, they are equivalent. They do exactly the same thing. Now, if you don't believe that, I show you. Here, we copy 0 to EDX, right? We can do something different. 2. Now try again. Is it still equivalent or not? Different. Now, if later I decrease now, what is the answer? Equivalent, right? We copy true to EDX, and later we subtract true from it, so it still make EDX 0. Now, if I insert some not semantic code here, let's see what happens. This one is NOP code, right? That's nothing. This one is also NOP code. That's nothing. Exchange CX with itself. And now see, still equivalent. Okay. Now the final demo here. Let's try again. Equivalent, right? Now I move this junction to here. Is this still equivalent or not? Let's see. Still equivalent. Now, if I replace this one with this one, copy 0 to EDX, right? So now, what is the answer? Still same, right? But is it actually same or not? Anybody tell me? Are they really equivalent? No, right? Because move 0 to EDX doesn't change any flux, but so EDX with itself change some flux. And here, okay, here's a copy from the Intel manual. Here, So change many flags like OF, overflow, side flag, zero flag, AF, parity flag, and CF, right? So actually SOR doesn't really do the same thing as move 0 to EDX. So here, equivalent. But now if you uncheck this, we don't ignore efflux register update anymore. We take that into account and see what is the answer now. Different. Because now we care about the flux. Okay, a few more minutes. I am back to the slide and just a demo. Well, OptiSig looks nice, but there are some limitations that cannot be shown now. First, you cannot do anything with the self-modified code, because what you are doing here is a pure static analysis, and static analysis cannot deal with the self-modified code. And if you have some indirect branches inside the machine code, we have a problem, because remember that LVM, they don't allow the indirect branch. And finally, the efficiency of SMT solver really depends on the complexity of the machine code. So if the machine code is very complicated, SMT solver can take a lot of time to run and to give you back the answer. That will be a problem. So the future work is that we try to show the limitation somehow. And maybe if we have time, we can try to implement the OptiSig for the real AV. You can use Clam AV, which is open source. So you can do that. And we will deploy OptiSig as an independent toolset for malware analyst people, so they can benefit from this tool. Okay, here come conclusion. Syntactic signature totally failed to detect the metamorphic malware. And we propose OptiSig, which is a semantic signature, and OptiSig can solve the problems of syntactic signatures, and we can detect the metamorphics, which use popular transformation, the 4 transformation I introduced. And here I use 2 key technology. First one is LLVM, which we use to normalize the machine code, and after that we optimize away many junk code inside. And to compare the signatures, we use the SMT solver, and we generate the logical formula from the normalized code to SMT logical formula, and after that we use the solver to verify the equivalence of them. Some references for you. Okay, so that's my talk, and any questions? Yes. Yeah. Yes. Right. Okay. So as I have a slide here. So in this talk, I just focus on the most popular transformation, which are simple enough for me to solve. For those code that are too complicated, the logical formula generated from the code can be very complex, and in that case, this method cannot might be not very suitable. So yes, that is still the open problem for us to solve. Yes, please.
In your examples, you don't use any code that does memory dereferencing, read the stores in memory. If I have 2 sequences of code that are identical, but
Yes.
the reference a global variable is at a slightly different location, how does that address of the global, which is effectively constant, affect the outcome of your comparison?
Okay, so in case of memory access, right? Memory access is another problem, because if we don't really know where the memory is, it's very hard to generate the logical formula for that. So in the case that the memory access to the some fixed address, you can easily generate the logical formula. But if it access to some indirect memory address, yeah, that's another problem. Thank you. So with this OptiSig, we try to, at least we know that is an open problem, which in theory cannot be totally solved automatically. So what we're trying to do here is that we try to raise the bar higher, so we can somehow detect some metamorphic malware, but not all of them. So any other questions? Okay, so thank you very much.